it's working. Yeah. So first, let me thank the organizers for giving me this opportunity to present my work in this very nice workshop. So today I'm going to talk about transport beyond the quasiparticle paradigm and theories of high-density superconductivity. Let me just acknowledge my collaborators in the topics that I'm going to present in this talk. So Van Wildo, who was my former PhD student, now he's a postdoc at the University of Minnesota. Catherine Pepin from CES Saclay, France. Rafael Caetano, who is my student from UFG, and Thomas and Xavier. Okay, this is the outline of my talk. So in the first part of my talk, I'll be talking about transport beyond the quasiparticle paradigm. And for that, I'm going to use this memory matrix formulas that I'm going to explain a little bit about that. Then I'll move on to a theory for the cuprates, this so-called SU2 pseudo-spin symmetry. And then I will briefly talk about loop currents also in the cuprates. If time permits, I will mention I'll talk about a model for the iron selenide compound. And then I will end my talk with the conclusions. Okay, so this is the universal phase diagram of the cuprates. So as you all know, the cuprates exhibit a plethora of phases. So here at low doping, you have the multi-insulating phase. Here you have the pseudogap phase, which onsets a T star here. Here you have the superconducting dome, which is unconventional, so it's D-wave superconductivity. And this is the most mysterious metallic phase, so this is the so-called strange metal phase that occupies a very large region of the phase diagram. And at very high doping, one recovers from a liquid regime, where resistivity is given by a quadratic term. Okay, you also have this charred order phase. So you see there are many phases that one has to explain in a unified way. And this is the quantum critical point. So yeah, that's it. So in this talk, I'll focus on this strange metal phase and also the pseudogap phase. And I will also talk about this charred order phase in the cuprates. So let's start. So the formulas that I'm going to use here is the so-called memory matrix formulas. So a very important message that I want to convey here is that a conventional approach of deriving a quantum Boltzmann equation to calculate transport potentially fails because the quasiparticles are not well defined in these materials. And so this is the motivation for this method. So the Moritz-Zwanzig approach to calculate transport. And the strategy of this method is the following. So only the operators with longest relaxation time scales that actually have a finite overlap with the currents will contribute to the conductivity of the system. And as you are going to see, the memory matrix is a generalization of the concept of scattering rate in Boltzmann theory, but it's applicable to systems in which this quantity is not well defined. Okay, so I'll start here with a model. So this is the so-called Spin-fermion model, which was described by many authors in the literature. Here, psi is the fermionic field, and phi is the bosonic field. Lambda here is the coupling, which describes interaction of the bosons and the fermions. And I'm going to include also this so-called composite interaction. As you see here, the fermions scatter of a composite operator here with two spin fluctuations. So this is important because, as you're going to see, this interaction couples to the whole Fermi surface of the system, whereas this spin-fermion coupling, the lambda, only couples to the so-called hotspots. So the hotspots are these spots here, are these points, special points, which are the intersection of the underlying Fermi surface of the system with the so-called antiferromagnetic zone boundary of the system. Okay, this I mentioned already. So yeah, this couples efficiently only to the hotspots, and this composite operator will couple to the spin fluctuations to the entire Fermi surface of the model. Okay, so we are going to introduce two types of disorder in this model. So if you don't include disorder, this Lagrangian here has no unclapped term. And actually, if you calculate conductivity from this model, as it stands, the result is infinity at any finite temperature. And the reason for that is that we don't have any source of momentum relaxation in the model. So we have to include a source of momentum relaxation, and for that we are going to specify this mechanism here, which will be impurity scattering. So we're including two terms. So one will couple to the fermionic fields, and the other term will couple to the bosonic fields. And this must satisfy this standard averaging relations here. Okay. Now, so this is a bit technical, so please bear with me here. I will define a matrix of generalized conductivities given by this expression here, where chi is the matrix of static retarded susceptibilities of slowly invariant operators in the system, n is a time reverse symmetry breaking, which is related to the application of magnetic field. For b equals to 0, this matrix vanishes. And the matrix of susceptibility is defined as, in a conventional way. And from that, we can calculate many things. So we can calculate electric conductivity, thermoelectric conductivity, thermal conductivity, so on and so forth. Okay, and the Feynman matrix is given by this closed expression here. L is the Liouville operator, which is defined by this expression, which basically, so L is related to the time evolution of the operators in the system. And this Q here is a so-called projection operator that projects onto a space of operators perpendicular to the slowly varying operators. Okay, so you don't have to worry about that. The only message that I wanted to leave here is the following. So the Feynman matrix encodes the mechanism of relaxation of all the conserved operators in the system. And due to this projection operator, this is actually a smooth function of the coupling constant, and it can be evaluated in a perturbative way. Okay, so we are going to do that. Using Noether's theorem, the operators with the longest time scales are the total momentum and the current operator, P and J. Then this is related to the fact that initially the system is invariant, so it's translational invariant, and it's also invariant to U1 symmetry, so charge symmetry. And from that, we can calculate the resistivity of the system, which is given by this here. And to leading order, the susceptibility is equal to the non-interaction susceptibility. So this contribution here has no temperature dependence, so the only temperature dependence will come from the memory matrix itself. Okay, so to calculate the memory matrix, one has to calculate many diagrams here. So we are calculating in a perturbative fashion. So here I show you all the diagrams that we have to calculate. So this is M0, M1, M4, M3, 5, so on and so forth. And as you see here, there are many different contributions. So this is a constant term. This is the t to the square term. This also depends on the ultraviolet cutoff. Lambda here is also independent of temperature. This is t to the fourth term. This is the linear term. So the linear term here, as you're going to see, is related to the inter-hotspot carrying, and this is going to lead to the linear resistivity in the model. So, okay, so to calculate the memory matrix here, and we do that, and as a result, we get this result. So, resistivity is given by rho naught, which is the residual resistivity, plus a linear term, which comes from the inter-hotspots carrying. This t squared term, which is, as I showed before, it's given here. So it's given by this term, which I include in the model. And also we get this t to the fourth term. This is, of course, subleading. So we are going to neglect this. And also another important point, it's A is much larger than B at optimal doping. So one recovers the linear resistivity for the model. And also another important fact is that the scattering rate of A is highly anisotropic and doping dependent, while the scattering rate related to the B factor is completely isotropic and doping independent. Sorry. Yeah, okay. So we have to include a cutoff. I didn't mention that. Yeah. So I have to include a cutoff. But this was a bit technical, so I didn't want to mention that. Yeah, we have to include that. Otherwise, it diverges. Okay, so, and this agrees with a phenomenology proposed by Nigel Hussey and collaborators, which is given in this paper here. Note that the A contribution is related to the inter-hotspots carrying, which means that if the Fermi surface lacks these special points, then one would recover a t squared term, so a quadratic resistivity. And does that make any sense? So I show you where he proposed a possible phase diagram for the cuprates. And so what we get is for the strange matter phase, one gets, in addition to the linear term, we get also a quadratic term here. Which is much smaller than this contribution. Of course, if you go to very high doping, there are no hotspots anymore because there are no intersection of the Fermi surface with the antiferromagnetic zone boundary. So one recovers the t to the square term. Of course, there is a crossover region here. And what happens to the pseudogap phase? So the pseudogap phase onsets here at t star. And as you know, hotspots are gapped out in the pseudogap phase. So there are no hotspots. No, we can show that. Yeah, we can show that. Yeah. Yes. Yeah. Okay, yeah. Yeah, I completely agree, yeah. Yeah, there's a cutoff, but I didn't want to mention that, yeah. Actually, it's a temperature-dependent cutoff. So, yeah, but I didn't want to say anything about that. Okay, but there will be a crossover regime where the t to the square term will become, of course, more important to the linear 2 term. Okay, so the hotspots are gapped out in the pseudogap phase. So one may assume on a phenomenological level that okay, the Fermi surface can be either Fermi arcs here or Fermi pockets, it doesn't matter. So according to this calculation, the resistivity should be given by a quadratic term inside the pseudogap phase. So one would obtain a Fermi liquid-like transport inside the pseudogap. Even though I'm not saying that the pseudogap is Fermi liquid, I'm just saying that it obeys a Fermi liquid-like scaling. Okay, so does this agree with the experiments? I'll show some experiments which suggest that this is the case. So this is the first spectroscopy evidence for Fermi-liquid-like temperature dependence of the relaxation rate inside the pseudogap phase. So I show you here the data of some related works also. So as you see here, the strange matter phase is given by linear resistivity. Here you can see clearly a crossover between this linear term and the quadratic term here. So you clearly see these two contributions, to linear T and T quadratic. And this also agree with the calculation. And in the pseudogap phase, you see here that there is a regime where the resistivity is also T quadratic. Okay, so this is also a very interesting result, which was produced by the group of Louis Taillefer. The A here is the prefactor related to the so this is the prefactor of the linear term. As you see here, right in the end of the superconducting dome, it goes to 0. And this would also agree with our scenario where the hotspots are the important driving force for the linear term. Okay. So we can calculate many other transport properties. So I show you here briefly some other quantities that we calculate using this memory matrix formalism. So we can calculate thermal conductivity, the so-called Peltier coefficient. And from this, we can estimate the temperature dependence of all the quantities which are given here. So you don't have to worry too much about that. And the main message that I want to convey here is that from these expressions, we can calculate many things. So we can calculate magnetoresistance, which is given here. So it's B squared. B is the magnetic field. And so it's B squared over T to the 4th term. And these are with experiments also, where you see that the cuprates obey the so-called Kuller's rule inside the pseudogap phase and also at optimal doping. We can also calculate the so-called Hall angle, which is given here. So we get two contributions here. We can also calculate Seebeck coefficient. And this is a linear contribution. This is also Fermi-liquid-like, Fermi-liquid-like term. But as we move on to calculate the Nernst coefficient, which is given by this expression here, we get a very non-Fermi-liquid-like contribution, which is given by C over T plus another constant over T squared. Okay, so most scaling forms which I derive here agree qualitatively with experiments, except for the Nernst coefficient, which there are no experiments so far over a large temperature regime, so that we cannot compare precisely what is the temperature dependence of this coefficient here. But apart from that, all the others are, let's say, more or less well established. Okay, we can also calculate the Wiedemann-Franz law using this scheme here. So I show you the Lorentz ratio of the model at intermediate temperatures. So the Lorentz ratio is given by the thermal conductivity, longitudinal thermal conductivity over the over T times the longitudinal conductivity, electric conductivity. This is given by a T squared term instead of the constant demanded by Wiedemann-Franz law. And what that means is this, what we obtain from our calculations is that the Wiedemann-Franz law is clearly violated within the strange matter regime. Of course, the Lorentz ratio is naturally expected to return to a constant value at very low temperature. So I emphasize here that we are at intermediate temperatures, because the effects of disorder will play a dominant role in this regime. Okay, so I will move on to another calculation that we did, which refers to this SU2 pseudospin symmetry in the cuprates. So I start very briefly describing the well-established evidence of charge order phase in the cuprates. So as you see here, there are many experiments which show unambiguously that the charge order is a real phenomenon that takes place in these materials. So from NMR experiments, you see this field-induced charge order phase inside the superconducting dome. Resonant X-ray experiments, they managed to see these charge orders above TC with no magnetic field. As you see here, this T CW is slightly different from T star. This is the pseudo gap temperature in YBCO. From STM and also X-ray experiments, they managed to establish that the order parameter related to the symmetry of the order parameter of the charge order phase is D-wave. So it's similar to the superconducting order parameter, and the modulation of these fluctuations are given by these wave vectors, which connect the so-called hotspots in the theory. And these are the axial wave vectors that I'm going to mention in a moment. Okay, so the standard model to describe this material is, of course, the Hubbard model. So I show you T and T prime Hubbard model on a square lattice. So the main question is in this field is, does this model contain enough physics for describing high TC superconductivity? And if yes, what is the heating order of the pseudogap phase? And many candidates enter the arena here. So there is this pair density wave phase that I'm going to talk about in a minute, which is a possible candidate for the pseudogap heating order. There's also the loop current phase, which I also mentioned briefly in this talk. There's also this fractionalized Fermi liquid proposal where topological properties enter in the description of the system. And there is, of course, this so-called SU2 pseudospin symmetry that I'm going to talk now. So this is the Spin-fermion model. So of course, we can decouple the Hubbard-U interaction in the magnetic channel by introducing Hubbard-Stratonovich. So by using the Hubbard-Stratonovich transformation, we can derive these Lagrangian for the system. So this is, of course, the Spin-fermion model, which was put forward by Abanov and Shubukov. So this model contains, of course, a D-wave pairing phase, and the pairing glue is given by the antiferromagnetic spin fluctuations and the system. But actually, the same glue leads to D-wave charge order phase. And this is related to this so-called emergent SU2 pseudospin symmetry. So this is an intrinsic symmetry in the model. And this was first pointed out by Max Metlitsky and Subisashdev in 2010. Later on, there was this very important proposal by Efetov and Catherine Pepin in 2013, in which they proposed that the pseudogap phase may be due to the fact that at high temperatures, the system cannot decide between the near-degenerate charge order and superconducting order. And what that means is this pseudogap order would be given by a matrix which includes both components of both the order parameter of the charge order fluctuation and also the D-wave superconducting order. Okay, so there are many consequences for this proposal, and there are many interesting predictions that agree with experiments, as I'm going to show in a moment. Okay, so what we do here, we use a complementary microscopic approach to describe the system. So we are going to use the so-called fermionic hotspot model. This is a purely fermionic analog of the Abanov-Shubukov spin-fermion model. And it includes all relevant interaction between all the all the hotspot fermions. And we are going to use an RG approach, which allows for all the instabilities of the model to occur on equal footing. And the most singular behavior, the most important behavior here occurs at the hotspots. So these are the special points here. And we are going to use this approximation of linearizing the energy dispersion around these points. And we can write down a partition function for the model, which is given here. So this is the kinetic term, and this is the interaction term. As you see here, there are only fermions. There are no bosons here. And this, of course, should be in the same universality class of the Spin-fermion model. And I will show you in a minute that this is indeed the case. So the parameterization of the interactions that we're going to use is the so-called 2D geology notation. So I show you many couplings between these hotspots. And to relate this effective model to the 2D Hubbard model, of course, one must impose that the G is initially proportional to the local interaction U. And we also have to define a ultraviolet cutoff here, which is given for simplicity by the bandwidth of the system. And we can calculate many things. So we are going to use a two-loop RG calculation for this model. And the reason for that is that at two-loop, so one needs to go at least a two-loop order in order to include self-energy feedback into the RG flow equations. So I show you here the self-energy of the model at one loop order. So this is the Hartree-Fock. This contribution has no energy dependence. And at two loops, one gets this so-called sunset diagram, which is the first non-analytic contribution to the model. And this diagram, we would normalize many things. So we would normalize the Fermi surface, the quasi-particle weight, the Green's function, the spectral weight, so on and so forth. So that's the reason why we have to go at least to two loop. But it's, of course, a more complicated calculation, as I'm going to show you. So we have to renormalize the couplings of the model, also the fermionic fields, and also the Fermi velocities, which are given here. And this is the ratio of the Fermi velocities. And using a standard RG condition for the Green's function, we can obtain this RG flow equation for the quasi-particle weight, given in terms of all the interactions in the model. And we can, of course, solve this numerically. But first, let me show you very briefly the diagrams for the vertex corrections in the model. So we have to calculate many diagrams. And as a result, we get many coupled RG flow equations of up to two loops. So this is schematically the RG flow equations for the couplings. I'm not going to show you all the details because the RG flow equations are really, really big. But they are not complicated to solve it numerically. So we are going to do that, and as a result, we get many non-trivial fixed points using this two-loop RG approach. But remarkably, all but one non-trivial fixed points are unstable. So only one is stable in all directions. So this is this fixed point here, which is very surprising. And this fixed point has an emergent SU2 symmetry. So what we mean by emergent is that the initial model is not SU2 pseudospin symmetric, but as the RG flows towards the low energy limit, the interactions that break the pseudospin symmetry flow to zero, and only the interactions that preserve the SU2 pseudospin symmetry remain finite. So this is very interesting and provides a microscopic calculation and justification of why this SU2 fixed point should control the physics in the low energy regime. So here I show you schematically the flow towards the SU2 fixed point in a model. Okay. And we can calculate many things. So here is the RG flow for the quasi-particle weight. L here is the RG step. As you see here, the Z flows to 0 at, in the low energy limit. And what that means is there are no coherent low-lying quasi-particle excitations near the hotspots. So that implies that we see a breakdown of fermi-liquid behavior near the hotspots in the model. And this was published in this paper here with my student in 2013. We can calculate other things. So using the Scalan-Zemanzik equation, we can calculate the renormalized Green's function of the model. And at the fixed point, this equation has this solution here. And from this solution, we can also calculate the spectral function of the model. Okay. One very important thing that I want to emphasize here is that due to this so-called SU2 pseudospin symmetry, when we calculate response functions in the model, we see that so there is this charge order phase in the model, but as a result of this emergent pseudospin symmetry, another phase arises, which is the SU2 partner of the charge order phase in the model. So we get a composite order parameter given by PDW/CDW in the system. And this is modulated, so this is bidirectional, PDW, CDW. And this is modulated by these axial wave vectors which connect the hotspots in the system. Yeah, this is a bit formal, so I won't go into detail about that. So this is very important. So what we see here is that this composite order parameter should naturally arise in this hotspot model. And this was published in this paper here. And of course, this should be visible in experiments. So here I show you, so first let me just explain very briefly what is this, what is this paired density wave phase. So this is a superconducting order with a finite Cooper parison of mass momentum. So it's similar to FFLO state, but it's zero magnetic field. Okay, so this of course should be visible in experiments, and this was seen in this very interesting and very important experiment by the group of Seamus Davis and collaborators in 2016. Here is the Nature paper where they detected for the first time a Cooper paired density wave in this BISCO. And they even cited us in the abstract of the paper. And what they did, so they were able to map out the Cooper paired density by using this STM machine. And by Fourier transforming this, they managed to obtain the modulation of the paired density wave, which turned out to be exactly given by the wave vectors which connect the hotspots. So this was, of course, very interesting, and it's an interesting prediction that naturally comes out from our model calculation. So you can see also here some follow-up works done by the same group, and this was very interesting. Okay, so now I'll change gears a little bit. I'll still talk about cuprates, but I'll mention very briefly some evidence of a new phase in these materials, which are so-called loop current phase here. And this was done by two different groups. So this is the group of Kaptulnik, where they did current rotation experiments, and they see an evidence of time reverse symmetry breaking at temperatures which are very close to T star here. And this was also done by the group of Philip Bush using polarized neutral scattering. So this is their data here. So as you see here, it's really, really close to T star. Here's the region of the experimental evidence of a charge, of short-range charge order phase here. And this, of course, is very important, and one should also try to describe why this is, why one sees this time reverse symmetry breaking in the system. So we try to model that and we used a different model. Sorry, so we used this three-band Emery model, which was proposed by Emery, Varma, Abrahams, Schmidt-Brink. And this is a three-band model. Here, as you see, one includes the copper orbitals and also the oxygen orbitals given here. So D is the creation and annihilation operators of the electrons residing at this orbital here, and P are the creation and annihilation operators of electrons residing at the oxygen sites. UD is a local interaction term inside the copper site. UP is the local interaction inside the oxygen site, and VPD is a non-local interaction between the copper and the oxygen site. So the two important parameters in the theory is this UD and VPD, as I'm going to show. Okay, so we were able to derive an effective theory. So we included here both so we restrict our model to the lowest energy band and also the hotspots of the theory. So we were able to derive a very complicated action for this model. And this is the Spin-fermion model, the conventional one, and R2 here is the other parameter related to the to the current order. Okay, so we produced two works about that. Here are the references, and okay, and these are the intra-unit cell currents in this so-called theta-2 loop current order phase, which was proposed by for the first time by Varma. And this state breaks C4 symmetry, so it's a nematic state. Also breaks time reversal symmetry, breaks parity, but it does not break chirality. And these orbital loop currents naturally yield a magnetic moment per unit cell. And what we did, so we did the mean field calculation for this model. So it's a very complicated model, so we were not able yet to use RG theory to describe the properties of the model. So we just did a mean field calculation, and here I show some results. As you see here, lambda is the spin-fermion interaction in the model. So as lambda grows, it promotes loop current order phase, which is given here. But as you see, this loop current order phase competes very strongly with this called charge order and PDW, and one refers to unidirectional charge order phase. So as we move on to bidirectional charge order phase and PDW, we see a similar behavior. So lambda promotes loop current order, but we see here a coexistence of these two phases. So loop current does not suppress the charge order phase and per density wave phase in the bidirectional case. So it suppresses in the unidirectional case, but it does not suppress in the bidirectional case. So we see here, at least at mean field level, that there is a possible regime where these two orders coexist, meaning so both loop current order and this composite charge order phase, pair density wave phase. Okay, so this was a mean field calculation. Of course, we have to improve that in order to include fluctuations effects, and this will be done in the future. Okay, I still have time. So I will briefly mention here a model for the so-called ioselenide compound. So the main question here is, what if we apply the two-loop RG framework to iron-based superconductors? So I will focus on this ioselenide compound. And this is based on this work that I submitted recently, and it's posted on the archive, which I did with my student. Okay, so why do we choose the iron selenide? So this compound stands out as having the simplest, one of the simplest lattice structures among the iron-based superconductors. And the lattice structure is given schematically here. But also a very interesting fact is that a monolayer of iron selenide grown on strontium titanate produces the highest TC among all the iron-based superconductors. And this, of course, hints at an unconventional mechanism at work in these materials. Here I show you the band structure of the system. So from ARPA's experiments, one sees that the Fermi surface consists of arcs, both hole pockets and not arcs, pockets. Hole pockets and electron pockets here, and they have very rich orbital structure. So this is dxy, dxz, and dyz. So it's of course a more complicated material, but it has some simple things that makes this material simple also from a theorist perspective to try to describe. So this is the phase diagram of the material. So this is temperature versus pressure. At zero applied pressure, one sees at around 90 Kelvin a tetragonal to orthorhombic transition here, and this is of course the nematic phase. And at very low temperatures, so this is around 8 Kelvin, this is superconduct. Here, as we apply pressure on the system, this nematic phase gets destroyed, and the spin density wave gets promoted as a result of this. And this reaches a peak here, then it suppresses again, and the TC increases dramatically as a result of pressure. So here, TC is around 37 Kelvin. And of course, one has to try to describe the interplay of all the phases in this system. And we are going to use a model to do that. And but first, let me also mention this very interesting experimental result from the group of Seamus Davis, which was published last year in Science paper, where they see an evidence of orbital selectivity. So these orbital selective superconducting gaps, so they were able to extract the quasiparticle weights from this data. And as you see here, the quasiparticle weights are anisotropically suppressed depending on the orbital. So this is ZXY, so it's almost approximately 0.1. This is ZXZ, 0.2. And this is ZYZ 0.8. And this is a signature of this so-called Hund's metallicity, which is a new state which is halfway between a conventional metal and a Mott insulator. And we want to try to obtain this result from a model calculation. So we are going to do that by using this simple model. So it's a multiband three-orbital model given here. As you see, I'm starting from a model with hole pockets and electron pockets with the exact orbital structure seen in experiments, and I'm able to parameterize all the interactions among these pockets. And this model was first proposed by Shubukov, Kodas, and Fernandez in 2016, where they used the one-loop RG calculation. And here we are going to use a two-loop RG. These couplings, they must be related on a microscopic level to of course, to the on-site Hubbard U, and J here is the Hund's coupling. Okay, so we can calculate many order parameters in the system. So here I just show you some important ones. So we calculate antiferromagnetic order parameter here, singlet superconductivity, and this UCS stands for uniform charge susceptibility, and we can also symmetrize this with respect to the pockets. So as you see here, there's singlet superconductivity with S++, so it doesn't change the sign of the gap when you move from the hole pocket to the electron pocket, and here is S plus minus, which changes the sign. This here, S plus minus POM, stands for Pomeranchuk instability with S plus minus symmetry, and this is D-wave Pomeranchuk. And we can follow the same approach, so we calculate self-energy and vertex corrections up to the loop. So I won't go into detail about that. And from that, we are able to obtain the RG flow equations for the couplings, which are given schematically here. And we solve numerically all these coupled equations, and we get this flow of the couplings as we move towards low energy limit. And here I just show you some couplings. Even if we start from very small weak coupling, it shoots up very quickly towards a strong coupling regime, meaning U of the order 1. And, but some couplings, they flow to 0. So we see this tendency here. And we can also calculate the RG flow for the quasiparticle, and we see here an orbital selective renormalization of the quasiparticle weight. And this is very interesting because we can only obtain that using this two-loop RG flow. And this is agrees qualitatively with the experiments. But of course, we have to do more. We have to make the model more realistic in order to obtain really precise agreement with experiments. Okay, but yeah. So what is the origin of this anisotropic renormalization? So we move on to, so I show you here the RG flow for the other parameter susceptibilities. So I put here the one loop RG and the two loop RG just to compare the two. And here you see the flow of all these other parameter susceptibilities towards the low energy limit. And in the one loop RG, you see that the D wave and S wave Pomeranchuk stability wins. The black line here is the ferromagnetic susceptibility. But of course, we have to go up to two loop to see this orbital selective renormalization of the Z factor. And this, of course, has an effect on the RG flow equation for the susceptibilities. And when we do that, the antiferromagnetic susceptibility wins. So this is the antiferromagnetic susceptibility. The second subleading instability is S plus minus singlet superconductivity. The third one is S plus plus, and the fourth and fifth one are S wave and D wave Pomeranchuk instability. So the main message that I want to convey here is that as a result of this self-energy feedback, the Pomeranchuk instability gets suppressed with respect to the other susceptibilities. So the origin of the nematic susceptibility in this case would be this stripe type antiferromagnetism and not Pomeranchuk instability. But of course, this is just a model calculation. Okay, so I end with the conclusions here. So I talked about two different materials in my talk. So in the first part of my talk, I talked about the cuprates, and I showed you that the hotspot model and its emergent SU2 pseudospin symmetry captures qualitatively many aspects of the physics of the cuprates. Based on this theory, a novel bidirectional pair density wave / charge density wave composite order was predicted, and this was subsequently confirmed by STM experiments. Many transport properties of these compounds are also qualitatively captured by the SCW quantum critical model, aka Spin-fermion model. With the addition of weak disorder using the memory matrix approach. And an important thing is the memory matrix does not rely on the existence of well-defined quasiparticle excitations in the model. And for the iron selenide compound, so I showed you that an orbital selective renormalization of the quasiparticle weight is obtained for a model for this compound within a two-loop RG scheme. As a result, our present two-loop RG theory may provide a framework from an itinerant picture in which the role of orbital selectivity to describe the physical properties of these materials are taken into account. So with that, I thank you very much for your attention.